Good afternoon, or morning, or evening, whenever you're watching this. Right now, we'll be working on section 7.7 from Blitzer's Introductory and Intermediate Algebra textbook for college students. This covers applications using rational equations and proportions. So we'll be looking at some problems involving motion, work, proportions, and similar triangles today. So I thought as a warm-up, it would be interesting to look at. This is actually a problem from beginning algebra or introductory algebra where you used a system of two linear equations with two unknowns. So a lot of times people sort of confuse this one with some of the other motion type equations. So I thought we could look at both types. So here we go. I'll just go ahead and work this one with you. If you feel very confident, feel free to pause the movie and do the warm-up on your own. So the first step to really almost any application problem is figure out what the heck is going on. So we might as well call that analysis. So for this one, we're talking about a motorboat. It's giving us some information here, and we need to find the boat's rate in still water and the rate of the current. Right? So we've got two unknowns here. So why don't we let x be the rate in still water, so that would be as if there were no current, and we'll let y be the rate of the current. It really helps to officially name the variables because otherwise things can get very confusing. Now, with motion problems, recall that distance equals rate times time. So you've got different measurements. So you've got with the current, also known as downstream, and you have against the current, also known as upstream. And it's nice to make a little box organizing everything. And you basically have, rate times time is equal to distance. So let's take a look at the information we've been given. When we're talking about initially when it says a motorboat traveled 36 miles downstream, that's all the top of the box with the current. And so it gives us a time of 1.5 hours, so 1.5 hours, and a distance is 36 miles. And the rate we don't know, but think about it. If the current is with you, isn't it pushing you along? So basically it would be your rate in still water, which is x, plus the rate of the current. Similarly, when you're going against the current, the rate of the current's pushing against you. So it'd be your rate in still water minus the rate of the current. So in this case it took 2 hours, and it says return trip, which was the same distance, so the distance will be 36 miles, right? So here we go. Step 2, you basically need to translate this bad boy into math, okay? So when we're translating this problem, remember we said rate times time equals distance. So the first rate is x plus y times the first time, which was 1.5, and that equals the distance of 36. Then we have the second equation. The rate is x minus y times the time, which is 2, is equal to 36. Now we can write a similar system, okay, which will be if we divide the first equation on both sides by 1.5, we'll get x plus y equals 24. So that's the same as that first equation. And then the second equation, when we divide both sides by 2, we get x minus y is equal to 18. So this is the system that will be easier to work with. So the third step is to solve. So what we had was, we had x plus y was equal to 24 and x minus y was equal to 18. Now if we were to add these equations together, we can eliminate the y variable. Do you see y minus y is 0 y's? So you get 2x is equal to 42, and then isolating x, which was that rate in still water, you get x is equal to 21. So back substituting that value, you can pick either equation. If you use x plus y equal to 24, we get 21 plus y is 24, which means y must be 3. So now you just need to state your conclusion in words, which is that last step of an application problem. So the rate of the boat in still water is 21 miles per hour, and the rate of the current is 3 miles per hour. And you're done. So if you need to put a box around something, this would be the final result. All right? How'd we do? I'm sure this is your favorite thing, I know, doing word problems. Okay, so here we go. Problems involving motion. So again, remember that distance is equal to rate times time. Rational expressions appear in motion problems when the conditions of the problem involve the time traveled, often, or the rate. So when we isolate time in that formula, do you see you'd basically divide both sides by r. So time would be distance over rate. Okay, so that's often what we'll use. So here's the first example. So let's do our first step 1 analysis. And it's often good to just look at the last sentence, right? We need to find the walking and jogging rates, right? So here it says, as part of an exercise regime, you walk 2 miles on an indoor track, then you jog at twice your walking speed. So we don't need to have 2 separate variables since the jogging rate has been related to the walking rate. So why don't we just go ahead and say, let x be the rate you walk. So now the chart is a little different, okay? So we're going to have walking and jogging. Now, they give us information about the total time, right, that spent walking and jogging is 1 hour. So basically, what we're looking for is we need to get an expression for the time spent walking and the time spent jogging. And when you sum them, that will equal to 1. So we have information about distance and rate. Okay. So why don't we just say distance, rate, and then the overall, each individual time is going to be the distance divided by the rate. Let me fix my box here. Okay, here we go. So let's fill in the box. We walked 2 miles. 2 miles walking. The rate, well, we name that as x. So time equals distance over rate. Let's just call that time 1. And that's going to be 2 over x. Now we look at the jogging. We jogged for 2 miles. The rate is double the rate for walking, so 2x's. So the second time is going to be 2 over 2x, which do you see is equal to 1 over x? All right, so let's translate this. So here we go. So we have a couple things going on. The overall time, call it capital T, is equal to T1 plus T2. And the overall time is equal to 1 hour. That was given in the problem. So we can equate those two expressions and say, oh, well, T1 plus T2 is equal to 1. But do you notice we have expressions in x for T1 and T2? T1 is 2 over x, and T2 is 1 over x. So here we will have 2 over x plus 1 over x equals 1. So we've translated that. So now let's solve that bad boy. Okay. So our third step is to solve. Now we have a rational equation, right? So we have the rational equation 2 over x plus 1 over x is equal to 1. So restrictions x cannot equal 0. LCD is x. Okay. So, solving, we multiply both sides by the LCD, and we get x times 2 over x plus x times 1 over x equals x. So the x's divide out for each of these, and we'll get 2 plus 1 equals x, 3 equals x. So that is the walking rate, right? So therefore 2x will be 2 times 3, which will be 6. So let's go ahead and answer the question. Step 4, conclusion. And you should check your results. For the sake of time, I won't be checking every result, but it's a good idea for you too, if you have time remaining on an exam, for you to check your results. So here we go. Your walking rate is 3 miles per hour, and your jogging rate is 6 miles per hour, and you're done. Okay? All right, so next up, we've got another motion problem. Right? Now this one, is a little tricky. The water's current is 2 miles per hour. So do you see, in this one, the rate of the current. So it's a little different from our warm-up problem. And a lot of times people start getting these confused. So just be flexible when you run into these types of problems. So go ahead and read through the problem. Get a first read so you can understand it. All right, so let's do our analysis. So I'm going to look here at the last sentence to see what I need to find. I need to find the canoe's average rate in still water. So hey, let x be the average rate in still water. All right, so here we go. Again, we've got, with the current, against the current. So with current, against current. And then again, distance, rate, and our time, each of individual time, equals the distance over the rate. Okay. There we go. So let's look at these distances. So with the current, which is downstream, 6 miles. The rate is going to be the rate in still water plus the rate of the current, which was 2 miles per hour. So that first time, time 1, is going to be 6 over x plus 2. Second situation, against the current, which is upstream, we're going 2 miles. And it's against the current, so it's the rate in still water minus the rate of the current, which is 2 miles per hour. So the second time will be 2 over x minus 2. Okay, so here we go. Let's talk about time. All right. In this problem, it's saying in the same amount of time. So this is kind of an important statement. In the same amount of time. So the two times are equal to each other. That's what that red statement is saying. So the red statement is basically saying, hey, time 1 equals time 2. So what we're really going to be setting up is something called a proportion. So, oops, in that the second step, translating to math, we're going to set these times equal to each other. So what will happen is we'll have 6 over x plus 2 is equal to 2 over x minus 2. So now we'll have our rational equation to solve. So step 3, solve. So restrictions. We've got a couple of them. X plus 2 cannot be equal to 0, which means x cannot be equal to negative 2. And x minus 2 cannot be equal to 0, so x cannot be equal to positive 2. The LCD is going to be x plus 2 times x minus 2. So now, when we start solving, we will have 6 over x plus 2 equal to 2 over x minus 2. Multiplying both sides by the LCD, that was x plus 2 times x minus 2. So notice that the x plus 2's will divide out on the left side. On the right side, the x minus 2's will divide out. We need to distribute the 6 through the x minus 2, so we'll get 6x minus 12, and that's equal to 2x plus 4 after distributing. Moving the x's to the left and the constants to the right, we will have 4x is equal to 16. So x is equal to 4. And if x is equal to 4, oh, and we didn't need to find anything else out. So we found that canoe's average rate in still water. So we just need to write our conclusion in words. The canoe's rate in still water. Actually, we should say average rate. So the canoe's average rate in still water is 4 miles per hour. And we're done. All right. Now, another type of application that yields a result of a rational equation to solve are work problems. In work problems, the number 1 represents one whole job completed. So if I can complete a job, say, in 2 hours, so equations in work problems are based on the following condition. The fractional part of the job done by the first person plus the fractional part of the job done by the second person is equal to one whole job completed. So one whole job completed. Now you got to be careful because sometimes you Example 3. Shannon can clean the house in 4 hours. When she worked with her son Rory, it took 3 hours. How long would it take Rory to clean the house if he worked alone? So here it's a little different situation than given in the original. So the trick is, as always, to name your variable. Okay. So step 1, analysis. So let x be the number of hours it takes Rory to clean the house alone. So basically, when we go into translate, this is what we'll have. So Shannon can clean the house in 4 hours. So what you think about is, if I'm cleaning at the same rate, what portion of the job is done in 1 hour? Good. A quarter of the job would be done in 1 hour. Now, when she worked together with Rory, okay, it took 3 hours. So what portion of the entire job would have been done in 3 hours? 1/3. So the working together is on the other side of the equal sign. Well, how long would it take Rory to clean the house working alone? We don't know, but we know that when they work together, this is the portion of the job that's done. Okay. So when we go to solve, restrictions, x can't be equal to 0, LCD, do you guys see it'll be 12 x's, right? So we'll have a fourth plus 1 over x is equal to 1 over 3, and then multiplying by the LCD, we will have 12x times a fourth plus 12x times 1 over x is equal to, so notice that the 3 divides out some of the 12, so we will get 4x on the right. So now, continuing, this 4 divides out some of the 12. This x divides out this x. So we will have 3x plus 12 is equal to 4x. If I subtract 3x from both sides, I get 12 equals to x. So if you ever meet Rory, don't tell him I did this example. The conclusion in step 4 is that it would take Rory 12 hours working alone to clean the house. So just to kind of recap, I mean, the 1/4 was the portion of the job I could complete in 1 hour. The 1/x is the portion of the job Rory could complete in 1 hour. And the 1/3 was the portion of the job that Rory and I could complete together in 1 hour. Right? So you can extend this to have more than two people or crews working together. So here's another example of a work problem. So let's see what we need to name our variable. So this one deals with a hurricane striking and rural areas without food or water. So 3 of the crews arrive, and one can dispense the supplies in 10 hours, a second in 15, and a third in 20. So if they were all working together, how long would it take them? So why don't we let x this time be the amount of time it takes all 3 crews to dispense supplies working together. So when we translate this guy, it'll be a little bit different because we have all the individual times, but we don't have the time working together. So the first one took, let's see, what was that? It was 10, 15, and 20 hours. So the first guy in 1 hour would have 1/10 of the job done. The second guy in 1 hour, or second crew in 1 hour, would have 1/15 of the job done. And the third crew would have 1/20 of the job done in 1 hour. Well, working all together, that gives us the portion of the job all 3 working together would have done in 1 hour. All right. So the third step is to solve. So let's see what our restrictions are. Again, I believe we're going to have x cannot equal to 0. And the LCD in this case is going to be, let's see, 10, 15, and 20. I believe the smallest number they multiply out to be is 60, and then we have x. So we've got our 1/10 plus 1/15 plus 1/20 is equal to 1/x. Our LCD was 60 times x. So when we solve, we'll have 60x times 1/10 plus 60x times 1/15 plus 60x times 1/20 is equal to, I believe we can divide out the x's there, so that'll be equal to 60. Let's see what we can divide out over here. So 10 goes into itself once and into 60 6 times. 15 goes into itself once and into 60 4 times. 20 goes into itself once and into 60 3 times. So we will have 6x plus 4x plus 3x is equal to 60. 13x is equal to 60. X is equal to 60 13ths. which is exactly equal to 4 and 8/13. But since we're talking about time, we might want to get an approximation. I found that to be approximately 4.6. And our conclusion is working together, the three crews can dispense food and water in approximately 4.6 hours. Okay? So there's a couple of examples of work problems. Now, sometimes we deal with problems involving proportions. So, with proportions, that means that one fraction is equal to another fraction, right? And so you can actually cross multiply these things. If you notice, it says the cross products A times D and B times C are equal. So once you have one fraction equal to another fraction, you can cross multiply to solve. So in example 5, I thought this one was kind of amusing. According to the authors of Number Freaking, in a global village of 200 people, 9 get drunk every day. So if we could extend this to the world's 6.9 billion people, how many of those do you think would get drunk every day? So let's check it out. Basically, the way we would set it up is, the proportion of drunk people to all people equals proportion of drunk people to all people. So in this case, our unknown would be the number of the world's 6.9 people that got drunk every day. So here, in this village, 9 people out of 200 people got drunk, and we can equate that to the 6.9 billion. So I don't know if you want to use scientific notation or just have it be, I don't know, we'll just say that's what, 6.9 million. So I got to do 3 more zeros. And then X is, we don't know the number that get drunk. So what they were saying is you can go ahead and you can cross multiply, which means that 200 times X is equal to 9 times the 6.9 billion. And then if you divide both sides by 200, you get this number. So if this proportion holds true for the world, what that means is so that would be 310,500,000 people get drunk every day. So next, you'll have to take statistics to see if this is a reasonable supposition. Okay, so next up, a person's hair length is proportional to the number of years it has been growing. After 2 years, a person's hair grows 8 inches. So for every 2 years, the hair grows 8 inches. Okay? The longest mustache on record was grown by Kalyan Sain of India. Sain grew his mustache for 17 years. How long was each side of the mustache? Well, what we don't know is the hair length. So do you see that that will be the unknown? But we do know the number of years. The number of years is 17. So we have, we have years to length, years to length. Okay? So here we go. To solve, we can cross multiply. So do you see we get 2 times x is equal to 8 times 17. So x is equal to 8 times 17 over 2. I just divided both sides by 2. So x is going to be, let's see, 4 times 17 is 68. So each side of Sain's mustache was 68 inches long. Can you believe that? That's a long mustache. Okay. So next up, we go into similar figures. Okay. So two figures are considered to be similar if their corresponding angle measures are equal and their corresponding sides are proportional. So in this example, and this often comes up when you compare, height to shadows of two different things, you can make two triangles that are really one's inside the other, and that setup can make it similar. So a 5th grade student is conducting an experiment to find the height of a tree in the schoolyard. The student measures the length of the tree's shadow and then immediately measures the length of the shadow that a yardstick forms. The tree's shadow measures 30 feet and the yardstick shadow measures 6 feet. Find the height of the tree. So here we go. Let's make a picture. So let's just say that this here is the height of the tree. Okay. So this will be, our analysis. And we can let x be the height of the tree. And actually I have room to work here, so I'll make this longer. Okay, so we've got this height, and then we've got its shadow that comes out, right? And we don't know. So this whole thing is x. I'll do it in green. So the green is x. Now we've got a shadow that comes out, okay? And the shadow of the tree measures 30 feet. Now we've got this little yardstick, okay? So the yardstick is just going to be a little bit here. So this is 3 feet. And keep in mind that the tree goes all the way down. You know, so this yardstick is inside, you know, the tree measure that we're doing. So that is 3 feet. And then its shadow, so I'll do its shadow in gray, is 6 feet. Actually, that's kind of thick. So that's 6 feet. So remember, the shadow of the tree measured this whole thing. So what ends up happening is you've got, you know, this triangle. Oops. You've got this triangle and then you've got this triangle. Okay? They both share a 90-degree angle, and these angles are the same based on properties of parallel lines. Okay, so here's a parallel line, and you would have the alternate, would it be alternate exterior angles, I think is what it would be. All right, so here we go. We have similarity, and we can now translate. So step 2, translate. And here we go. So we have the height of the tree is to its shadow, as the height of the yardstick is to its shadow. And then we can cross multiply when we solve. So that'll be our third step, is to solve. So we had x over 30 equals 3 over 6. So cross multiplying, do you see we would get 6x is equal to 90, and x is equal to 15. So our conclusion, the height of the tree is 15 feet. Okay, and that wraps up our lesson for today. So as always, go do your homework that relates to this section, at least some of it, so you can cement in your mad knowledge, and have a fabulous day.